Welcome to Mr. Hobbs' AP Chemistry class. This is Monday, December the 5th. Today's topic is bond enthalpy, which we call bond energy or the heat of the reaction. And on Friday we learned that we can calculate delta H of the reaction using the simple equation of the sum of the heat of formation of products minus the sum of the heat of formation of reactants. So if we look at number 69 on page 209 in your old book, we see the thermite reaction. Okay? So what do we need to do here? Delta H of the reaction is equal to what? Products minus reactants, so it's going to be 1 mole times what's the heat of formation of Al2O3? Negative 166.9.8, and that's kilojoules per mole. Plus, what is it going to be for iron? 2 moles times 0, because the heat of formation for all elements is 0, minus reactants, 2 moles of aluminum times 0 plus 1 mole times the Fe2O3, which is going to be negative 822.16 kilojoules per mole. So now we just add all those together. Delta H of the reaction turns out to be how much? Negative 847.64 kilojoules. So what's the negative sign mean? Exothermic. Okay? So this is the amount of energy when 2 moles of aluminum and 1 mole of Fe2O3 are released, or reacted. This much energy is released. Okay? Now, when we did this reaction, I used 600 grams of this and 90 grams of this. So my question is then, how many grams or how much energy total was released during the reaction? How do we calculate that? I'm going to put it in red. 600 grams of this and 90 grams of this. How do we do this? Stoichiometry. Okay? So if I'm given grams of both things, what's the first thing I probably need to do? Find the limiting reactant. So why don't you do that? It's a great review for the exam. If you want to see this reaction demo, go to Mr. Hobbs. Look for Mr. Hobbs Does Thermite Reaction on YouTube. Feel free to subscribe. Yeah, I think I need more than 10. Yeah. No. So what are we doing to find the limiting reactant? Converting grams to moles. Then what do we do? Divide by the coefficient. So what do we get for the aluminum? Just the moles, not before you divide by 2. 3 point what? 34 moles of aluminum. But we divide by the coefficient 2, so it comes out to 1.67. And then for the Fe2O3, 3.76. So what's my limiting reactant? Okay, so aluminum is the limiting reactant. So that's the one that's going to determine how much product gets made. That one's going to determine everything. So then we can say, now again, we always want to start with the 3.34 moles. But what's the conversion factor now that we have between energy and moles? This right here. This is kilojoules. This many kilojoules when 2 moles of aluminum reacted, when 1 mole of Fe2O3 reacted, or when 1 mole of aluminum oxide was made. So we just use this then as a conversion factor. So we're going to say negative 847.64 kilojoules, but that's per 2 moles of aluminum. And that's going to tell me the total amount of energy that's released. And it comes out to negative 1415. Okay, we'll just say 14, we have 3 sig figs really here. Negative 1415, and that's the moles cancel, so that's just going to be kilojoules. So that's how much energy was released. Now that amount of energy isn't like an incredible amount for it to make the iron quite so hot. What was the other factor, do you think, that made the iron to where it was molten iron when it came out of the reaction and went straight through our cake pan and did all that? Okay, well the aluminum oxide, the iron oxide actually supplied the oxygen. Okay, but how long did the reaction take to happen, the whole thing? About 5 seconds, right? So all of this energy was released almost instantaneously. And so the iron just caught that energy and it just got super hot, just absorbing this energy, and it was kind of all compressed, so it was not really being released a lot to the surroundings, and so it just all kind of absorbed it itself and made the iron super hot. Part of the reason it gets so hot is the speed of the reaction. All right? So we can just do products minus reactants. Are we good with that? Do we need more? Do more? Or it's pretty straightforward. You just look up the number in the back of the book, plug it into the formula. Okay? So the key is you just multiply by the coefficient. Make sure of the state that you use. Okay? That it's got to be the same state. Now, let's look at using this. Let's do one more practice as far as using it as a conversion factor. If you stay on page 209 or let's see. Let's turn back a page and look at number 37. And Riz, well, you lost yours. Arez, you're the one that says you have it on your phone, right? You emailed it to me. Yeah, I may put that one on too. That one's only a 10-second little video. The other one that's currently on there is from way back, like 5 years ago. It's a pretty good one. Okay. But I have to say that y'all's one the fire pot caught on fire, right? That is the best one in a long time, as far as just the extreme amount of heat and everything going through. And that is the total amount of energy that was released when 600 grams of Fe2O3 combined with 90 grams of aluminum. So in our demo that we did, that's how much energy was released. So this is how much is per mole, just as a standard value. But now we can apply it, and that's kind of what this problem is going to be about. Apply it to how much energy is going to be released than when we used any amount. So now we have a conversion factor, because this tells me how many kilojoules per mole of Fe2O3 is going to be released. So if I have 2 moles of this, it's going to be twice that amount of heat. So if we look at number 37, is that page 207, 208? What page? It says 2 magnesium solid plus O2 gas goes to 2 MgO solid. But then out here it says that delta H of the reaction is equal to negative 1204 kilojoules. Okay? Now what does that mean? So the first question is it exothermic or is it endothermic? How do we know? It's a negative sign. Now if I wanted to include the energy, I wanted to do a thermochemical equation. I wanted to include the heat into the equation. Where should that 1204 go? Right side or left side? Okay, that was such confidence in that answer. Why right side? Because energy is being released, right? It's being given off like a product. It's being produced like a product. Whereas in an endothermic reaction, you need the heat in order to cause the reaction to occur, so it's like a reactant. So we could put it in like this. Now the key is that if I put it into the equation, you don't put it in as a negative. It's the side of the equation you put it that determines exothermic here, endothermic here. But it'll be positive on both sides. Now, again, if you want to compare, if it's positive here and you brought this to this side and compared it to the positive endothermic, what's the sign going to be on exo on this side of the equation? Negative. So if we're comparing, apples to apples, same side of the equation, the endo is positive, the exo is negative. So it's like you can be thinking you're taking it out of the system, but we put it positive over on the right-hand side. Y'all are comfortable? Does that make sense? Most of the time you'll see it like this, but sometimes it's here. So if it's on the right-hand side, you need to know that if you put it into the equation or try to use it, it needs to be negative. It's exothermic. All right. So that's A. Now B says, what if we have 2.4 grams of this? We want to know how much heat's released. What do you think we do? What does this tell me? Per 2 moles of magnesium, right? 1 mole of oxygen, but 2 moles of magnesium. So that's my conversion factor. So what do you think I need to do to the 2.4 grams? Convert to moles. So 2.4 grams of Mg times 1 mole over 24.3 grams. Now I have moles, so now I can use my conversion factor of negative 1204 kilojoules for every 2 moles of magnesium. This comes out to negative 59 point something. Negative 59.5. So, what does that number mean? Go to the environment when basically when 2.4 grams of magnesium is burned. Okay, because we're combining it with oxygen, that's generally burning. So you burn the magnesium, the metal strip, that's actually what we use to ignite the thermite in our reaction. This is that, we burn the magnesium. You guys, we've done that a bunch of times in Chemistry 1. Okay? So that's how much heat is released when 2.4 grams. Now, an alternate way to do that, it's really the same way, just a different perspective. You can say then 2 moles of magnesium is going to be 48.6 grams, right? So we could say that 48.6 grams of magnesium released 1,204 kilojoules. So 2.4 grams is going to release how much? Okay? I would say it's going to come out to negative 59.5. But so how do we solve for x? Cross multiply, so x is going to equal 2.4 grams times negative 1204 kilojoules divided by 48.6 grams. Right? I mean, I just cross multiplied and then brought the 48.6 over. And so notice 2.4, okay, divided by 2 times 24.3, which is 48.6. So 2.4 divided by 48.6 times 12.04. This is 2 moles of magnesium. It's just 2 times 24.3. Okay? So it's just, notice we're really doing the exact same thing. It's just setting it up as a proportion rather than with the units, to whichever way makes most sense to you. So now C says, okay, well what if we want to make delta H of the reaction to be negative 96? Is that what C says, negative 96 kilojoules? How much is required? So negative 96 kilojoules, and we want to know, well, how much MgO do we need? Okay? Might need a new calculator. How do we do that? How is that problem going to compare to this one? This one we were given grams. What do we find? Kilojoules. What's this one giving us? What are we looking for? So what do you think? Just go reverse. Back it up. So what should we start with? Okay. So now I need to find something that has kilojoules in it. What has kilojoules in it? The red, the 1204, right? So where should that go? So what is that? And we're looking for this one, right? So this is going to be 1204 kilojoules per 2 moles MgO. So that's going to tell me how much energy is going to be released, or how many moles of MgO I'm going to need to release the 96 kilojoules of energy. But I want grams, so how do I go to grams? How? Use the molar mass, divide. Am I multiplying? Am I dividing? What am I doing? You want 1 mole on the bottom. What's on top? Molar mass of this is 24.3 plus 16 is going to be 40.3 grams over 1 mole. So now I have grams of MgO, which is what I want. So you stick a fork in it because you're done. That's how you tell something's done. You stick a fork in it. It comes out clean. It's done. You don't have to do that when you just microwave food. No. No. Okay. So what do we get? Things that go on in his head. The rest of us will never understand. All right. What do we get? 6.43 grams. So what does that mean? So if you were to burn 6.43, or if you burn enough magnesium to make 6.43 grams of MgO, then you would release 96 kilojoules of energy in the process. Okay? So you would need, in order to release 96 kilojoules, you'd have to make 6.43 grams of MgO. Now D says how much energy is required to decompose, what's the 7.5? Now, oh really? To decompose this, let's just give me 1 second. To decompose this, what does that mean about the direction of the reaction? It's going this way. So what's the only thing that's going to change for our delta H? It becomes positive instead of negative because products have become reactants, reactants have become products. The only thing that changes is the sign. Okay? And we'll look at that when we come back because I want to look at that graphically as well.